Hello everyone, welcome back. In the last few classes, we derived the governing equations for fluid flows, and we saw the incompressible flow limit and the compressible flow limit. For the compressible flows, we learnt that we require all three equations: mass conservation, momentum conservation and energy conservation. And also to close the equations, we needed the ideal gas equation for the ideal gas flows. Okay, or any relation between the pressure, density and the temperature. In today's class, what we are going to do is we are going to non-dimensionalize the equations. So, why it is important to non-dimensionalize equations? It is very essential. You will see that in some of the CFD applications, the parameters that will be given to you are basically the non-dimensional numbers. For example, the Reynolds number, Mach number, maybe the Prandtl number, okay, and so on and so forth. And you will be asked to basically find the forces, okay, maybe the lift and drag coefficients, okay, the pressure coefficient, the skin friction coefficient, drag, etc. Okay. So, in those cases, how do you, if you look at the equations, all the equations have your the velocity, pressure, density, temperature, etc., right. But the non-dimensional numbers do not appear in those equations like Reynolds number and Mach number, etc., right. So, how do this flow vary according to these non-dimensional parameters, right. So, it is very important to cast these equations in terms of these non-dimensional numbers, and then you will see that how the variations of these in these particular numbers, your equations or your forces are basically changing. Right, you might have learned about the laminar flows, turbulent flows, transitional flows, and if the Reynolds number is low enough, it will be laminar, and there will be a certain amount of drag if the flow is laminar, especially the skin friction drag will be lower. If the flow becomes turbulent, the drag becomes higher, right. So, these findings that we have from the experiments should also be separated by the governing equations, and they are indeed supported, and you can actually directly see it also. Some of you might have taken courses in boundary layer theory, and you might have basically derived the boundary layer equations, and you might have made some approximations that the variation in the y direction is much higher than the variation in the x direction, and you might have derived the boundary layer equations. So, by using similar kind of basically analysis, we can find and derive the non-dimensional equations. This is also important from the point of view that if you look at, let us say, a real flight experiment, and let us say what is happening in a wind tunnel, right. So, in the flight experiment, let us say you are flying in an A320 and you have certain amount of drag and certain amount of lift and certain amount of moment forces, right, moment coefficients, right. But before it was designed, it must have been basically experimented, or it must, I mean, the parameters must have been evaluated in the wind tunnel, right. Now, fitting that kind of aircraft in a wind tunnel is very difficult, right. The size is too big, and in order to basically exclude the wall effects and all other things, you need to have a wind tunnel which is like at least 4 times the size of the aircraft, right, and building that wind tunnel itself is very expensive, right. So, how do you basically experiment that kind of situation, right. So, what you can do, you can use a scaled down model, right. So, basically the same aircraft, the same wings, same empennage, same control surfaces, same flap, slats and everything that you have in A320 will be there in your scaled down model, right. But how do you basically correspond, so you will get some result from the wind tunnel, but how do you make a relation with what is happening in your real flight situation, right. There must be some number that is governing the dynamics, right. So, that you can say that okay, what is happening in this model must also be happening in your real prototype. Okay. So, we will look into that. So, before we go into the non-dimensionalization, I want you to first talk about the similarity or the similitude. Okay. So, what is similitude? Basically, it is about making a relation between the prototype and a model, okay, under certain constraints. Okay. So, there are 3 kind of similarities, okay, as you can see here in the slide. Okay, one is your geometric similarity. Okay, this is geometric similarity. The second is the kinematic similarity, and third is the dynamic similarity. Okay. We will look into all these aspects one by one. Okay. So, what geometric similarity says, that the shape of the prototype and the model must be the same, okay, not the size. The shape must be the same, and the model can be basically scaled down or maybe scaled up also, it's up to you, by same factor everywhere. Okay. So, for example, if you see this example here, so this is a wing here, okay, and it has like if you can see, there is a chord length is around 8 meter. Okay. So, it is scaled down by 0.1. So, this is now become 0.8 meter, right. What was 8 meter here, this is in the prototype, now become 0.8 meter. So, this is scaled down by 10th factor, right. So, the same should be followed everywhere. Let us say if you have a maximum thickness somewhere which is 1 meter here, it should become 0.1 meter. Okay. And if it is 40 meter in the span, it becomes 40 by 10, which is 4 meter in span. Okay. Okay, not only that, it should maintain the same angle of attack, right. So, if it is at, let us say 10 degree angle of attack here, okay, it must be the 10 degree angle of attack here. Okay. That means, it should be of the same shape. Okay. So, let us say if you have an aerofoil like this, okay, which is let us say a chord length of 1 meter, okay, at an angle of attack of some degree, let us say 30 degree, and if you are trying to have the geometric similarity of let us say 1 by 100, right. So, then you will have an aerofoil which is small, okay, which is 1 centimeter, right, and then the angle of attack should be the same, which is the 30 degree. Okay. And then if you have the geometric similarity, okay, and then we can talk about the kinematic similarity and the dynamic similarity, but the geometric similarity is the first prerequisite or the precondition for the kinematic similarity and the dynamic similarity, right. So, now that we have the geometric similarity, that means the model and prototype have the same shape and the model has been scaled by the same factor everywhere in all the dimensions, right. We can talk about the kinematic similarity. So, what does the kinematic similarity says is that at two corresponding points, okay, between the model and the prototype, okay, the velocities are in the same direction and must be scaled by the same factor, okay, at any two location. So, let us say this is on this particular wing, we are talking about a height, okay, let us say we are talking about a height, let us say somewhere here, okay. Okay. This is in the, if I can say, this is in the z direction, okay, let us say, okay, this is in the y direction, okay. Let us fix our coordinate system, so that it will be easy to explain. Okay. So, let us say this is my x in the chord y direction, y in the vertical direction, okay, and z in the span y direction, right. So, at some height in across the boundary layer, let us say maybe the 0.05 mm, okay, you are measuring some force, let us say you are measuring the velocity, right. So, some point let us say your velocity is in this direction, okay, somewhere, okay. So, if you are doing it same on the prototype, okay, so because it is scaled by 0.1 in the prototype, you have to go to the height, okay, which will be let us 0.0005, okay, because it was 0.05 here, so now it is 0.005 meter, okay, because we have to the velocities at the corresponding points. So, whatever distance you have here, you have to take the 1/10 of the distance here in this direction, and then you can talk about the forces here, okay, and the kinematic similarity says that the velocity should be in the same direction, okay, and it must be scaled by the same factor. So, here you have taken the factor is for the geometric similarity, you have taken the factor of 1 by 10. So, the factor is 1 by 10 here between the model and the prototype, right. So, model is prototype by 10, right, but that need not be the factor for the velocity also, it can be 1/3 or 1/2. So, for this is for your geometric similarity. For the dynamic similarity, your velocity may be, let us say if I say V m by V p, it may be 1/2, right, but that will be followed everywhere, right. So, at every corresponding point in the domain, your velocities will be scaled by the same factor. Okay. So, that is your kinematic similarity, and last one is your dynamical similarity. Okay. So, before you go to the dynamical similarity, there is one thing I want to mention which is not often emphasized, is that for the kinematic similarity, it is very important that the flow should be in the same regime. Okay. So, whether the flow is in laminar regime or the transitional regime or the turbulent regime, that matters a lot. Okay. So, you should not be comparing, let us say you have a critical Reynolds number. So, the critical Reynolds number is the Reynolds number at which the flow basically transitions, okay, from a laminar flow to a transitional flow and then eventually to the turbulent flow, right. So, let us say you are talking about a number which is in the transitional regime, then it will be very difficult to basically correspond a prototype to a model unless the prototype is also in the same regime, right. So, if we are talking about laminar, the both should be in the laminar regime. If we are talking about turbulent, both should be in the turbulent regime, right. And transitional flow, particularly where the transition happens very fast, you have to be very careful that whether you are talking about in the laminar regime or in the turbulent regime. You might have heard in your fluid mechanics course about the drag crisis, that the drag increases and suddenly the drag drops down as the regime changes, right. So, those things we need to be very careful about. Okay. Now, this is about your kinematic similarity. Now, last one is the dynamic similarity. So, the dynamic similarity says is that at two corresponding points, let us talk about the same corresponding point here, or we can basically take an example of let us say two circles or two aerofoils. Let us take the example of two aerofoil here, okay, that I have drawn here already, and we are talking about two forces here. Okay. Okay, let us say the forces here and here. Okay. So, the dynamic similarity says that at corresponding points, the forces on the body should be in the same direction and this must be scaled by the same factor, right. And again this factor can be different from what factors that we have used in the geometric similarity or the kinematic similarity, but the same factor should be applied everywhere in the domain. Okay. So, that is what is the dynamic similarity. So, the forces should be identical, okay, and they are parallel in the sense that they are in the same direction and scaled by the same factor everywhere. So, now for the dynamic similarity, okay, you must have the geometric similarity and the kinematic similarity. So, if these two similarity are satisfied, okay, then you can talk about the dynamic similarity. Okay. So, how does it help is that like the example that we gave that, okay, let us say that we cannot this is your real prototype and this is the model that you can use in the wind tunnel test. So, you have done the testing on this model and you got some forces, but you know that these forces are a factor of what is happening actually in your prototype. So, you can just multiply that by that factor and you can find out the actual force that is experienced by the wing, right. Or you can talk about the velocity field and if you know the factor you can find that out. Okay. And so, if you look at many curves, okay, in the fluid dynamics literature, okay, you will find out, for example, there is a Moody's chart, okay, which says that how with the Reynolds number, okay, your drag is changing, right. This is in this side of Reynolds number, this is your side of drag, okay, and then let us say this is how your curve looks like. Okay. So, this is the famous Moody's chart. Now, you might ask question that Reynolds number is a function of many different parameters, okay, rho u L by mu, you must have read in your fluid dynamics your density, velocity, length scale and the viscosity, okay, and here is the CD is basically d by let us say half rho u square, okay, and maybe the L square also if you divide by area, okay, or some area. Okay. So, you might ask the question that let us say in this model I have the length is small and here the length is higher, then how do we talk about the correspondence, because uh, the density is different in the model, the velocity is different in the model, the viscosity is different in the model. So, what the dynamic similarity says is that as long as your length Reynolds number, which is the governing parameter here, governing non-dimensional here, which basically dictates the dynamics, right. So, as long as your Reynolds number is same between the model and the prototype, okay, regardless of what is the length scale you are using, what is the velocity scale you are using, what is the density scale you are using, you are going to same experience get the same drag, which is given as the CD here, right. So, that is how you can basically make correspondence between your simulations, your experiment and your theory, right, because all the flows are basically governed by some or other non-dimensional parameters. Okay. So, let us look at some of these non-dimensional parameters. Okay. So, the first and the most important parameter for the people who are interested in CFD is the Reynolds number, right, and I am sure you know the Reynolds number by now, okay, through your fluid mechanics courses, because if you are taking this CFD course you must have taken a basic fluid mechanics course, and if in any basic fluid mechanics course the first thing that you learn about is the Reynolds number. So, what is Reynolds number? So, Reynolds number is given as R is equal to, here it is given rho V L by mu, right. So, you can write it as rho V square divided by mu V by L, right, and then you can multiply this entire thing by L square, which is or some kind of area. Okay. So, this is equal rho V square L square and mu V by L. So, what are these two things? Okay. Let us look at the bottom one first. Okay. So, what is this? So, if you know, if you have know the boundary layer, okay, and if you want to find out what is the drag experience here, okay, the skin friction drag or the viscous drag. So, you say that you can find out the shear stress, which is tau w, which is basically mu del u by del y at y equal to 0, right. So, this is your viscous force, right. So, mu multiplied by some velocity gradient. So, if you write in terms of dimensional numbers, this is like mu v by L, right. So, it represents your viscous stress. So, mu v by L is a viscous stress multiplied by the area. So, stress multiplied by area is the force. So, this is the viscous force. And what is this rho v square? Inertial force. We have just derived the momentum equation, and if you see the second term, that has the velocity coming twice. Okay. So, that is your inertial term. So, this is your inertial force, that means how much is the contribution of the velocity that is coming in divided by how much factor the viscosity is opposing that, right. So, that the ratio between the two force, this is your inertial force divided by the viscous force, okay, and the ratio of the two is called the Reynolds number, right. So, if the Reynolds number is very, very low, that means your viscous force is dominating, right. Basically, the inertial forces are not that strong to basically find out the basically to have the flow overcoming that viscous nature, right. And on the other hand, if you go to the higher Reynolds number, so the viscous forces will be small. So, the boundary layer that is forming on the body will be very, very thin, okay, but at the same time you will have the flow gradient changing in the very, very thin region. Okay. So, this is a very important number, okay, given by Reynolds. Okay. This also tells whether the flow will be in the laminar region or in the turbulent region, right. Similarly, we have for the compressible flow, we have seen the importance of Mach number. The Mach number tells whether the flow is going to be incompressible or compressible, right. In terms of number, you can write Mach number as ratio of inertial forces versus the elastic forces, and elastic forces can be related to the compressibility, Okay. We have earlier derived how the speed of sound can be related to the compressibility, right, basically isentropic compressibility. So, you can basically derive that and you will see that Mach number is related to the inertial forces to the elastic forces. So, these two are the these two numbers we will be talking again and again in our course. Okay. But then there are some other situations where other numbers may become important. Okay. For example, there is a fluid number, okay, which is given by V square by GL, or you can write it as rho V square by GL and you multiply by area. Okay. So, that is basically this is the inertial force, and when the gravity is important, this number becomes very very important, and so the bottom is the gravity force, right. So, all these numbers tell you that it is an basically interaction between two forces and which force is dominating at a given situation, right. So, let us say if the fluid number is low, then your gravity force is dominating over the inertial force. If the fluid number is high, the inertial force is dominating over the gravity force, right. So, depending on the situation or what kind of fluid flow that you are trying to simulate, you have to look for the forces which are dominant in the flow field, and then you basically balance them out. Okay. Similarly, you have this Euler number, which is basically the pressure forces to the inertial forces, right. So, you know there are pressure terms also and the inertial term also in your Navier-Stokes equations, and you take the ratio between the two. Okay. This is the pressure is delta P. So, there is some pressure gradient there. So, your Euler number will be delta P by rho V square on pressure into area, that gives you the pressure force, and rho V square into area, okay, that gives you the inertial force, and you have to see that how they balance out each other, right. So, if Euler number is higher, then pressure force is dominating and vice versa. And similarly, if you have surface tension present, then you talk about the Weber number, okay, and here the it is a ratio between the initial forces divided by the surface tension forces, right. So, depending on the situation, these numbers are very useful, particularly for a Weber number if you are in chemical engineering and trying to do simulations, and if you have a free surface, okay, in those cases you worry about this Weber number. Okay. Similarly, if you have a flow which is dominated by the gravitational force, right, then you talk about the fluid number. Okay. Let us now talk about a case where we talk about the dynamic similarity. Okay. So, we will give an example so that the concept of dynamic similarity gets clear in your mind. Okay. So, the problem is that consider the flow of two geometrically similar aerofoils. Okay. The geometrically similar means that the geometric similarity is maintained. That means that two aerofoils are basically scaled by some factor. So, here it is given, one having 4 times the chord of the other aerofoil. Okay. So, the model is basically 1/4 time of the prototype. Okay. So, remember we are talking about the scaling down in the model, because that is what is generally practiced. You want to have a smaller section in your wind tunnel than what is there in the flight, but it is not necessary, you can have a scale up also. So, as long as you can maintain the Reynolds number and the Mach number, for example, then it does not matter whether you scale down or scale up. Okay. And the free stream parameters are very different, such that your V 2 equal to V 1, rho 2 equal to rho 1 by 4 and T 2 equal to T 1, 4 T 1. So, are those flows dynamically similar? So, let me V 2 equal to 2 V 1. So, shown here that the one having the 4 times the chord of the other aerofoil, right. So, let us draw these aerofoils. So, this is your small one, let us say this is your big aerofoil. So, this is the chord of C, this is your chord of 4C, right. This is 1 and this is 2, right, and then what it says V 2 equal to 4 V 1. So, this V 2 equal to 4 V 1 and then rho 2 equal to rho 1 by 4 and T 2 equal to 4 T 1. Okay. So, basically if the temperature is involved, it is a compressible flow. So, let us take the ratio of RE1 versus RE2. So, what we need to match is that RE1 should be equal to RE2 and M1 should be equal to M2, right, for the dynamical similarity. So, let us take this example RE1 by RE2, right. So, RE1 is rho 1 V1 C1 by mu 1 and RE2 would be 1 by RE2 is mu 2 by rho 2 V2 C2, right. So, express everything in terms of the 1, okay. This is rho 1 V1 C1 by mu 1, okay, and then mu 2 would be, let us write mu 2 here only, rho 2 equal to rho 1 by 4 in V2 is 4 V1 and C2 is equal to 4 C, right, or if I can call it C1, this is 4 C1, right. So, the rho 1 cancels out, B1 cancels out, okay, this 4 cancels out, okay, and then you will have mu 2 by 4 mu 1, right. So, this is the ratio between RE1 and RE2, right. Just V2 equal to 2 V1, right. So, V2 is 2 V1, 2 V1. So, if you do that, this is 2 V1, these 4 cancel out. So, this is mu 2 by 2 mu 1, right. Now, you know that the variation of mu, you know the Sutherland's law. So, it goes as mu equal to some mu reference multiply by t to the power 3 by 2 by t plus s, okay. This is the Sutherland's law that we have discussed. So, roughly because this is t to the power 3 by 2 and this is t, so you can say roughly mu varies at t to the power half, right, square root of 2, right. So, mu 2 can be written as t to the power half, okay, and some other factors which is constant for both the s and t1 to the power half, right. So, this is t into t2 by t1 to the power half and t2 by t1 is 4. So, 2 into this is 1 by 2 1 by 2 t2 by t1 to the half, which is 2 into 1 by 2, right, because t2 by t1 is 4, right. So, this is equal to 1, that means your RE2 equal to RE1, right. So, in terms of the comparison of Reynolds numbers, both are similar, right. Now, let us look at the Mach number, okay. So, let us look at the Mach number, I will just do it quickly here. So, RE2 equal to RE1. Now, we want M1 by M2, right. So, M1 is basically V1 by square root of gamma R T1, okay, that is square root of gamma R T2 by V2, right. This is V1 by V2 into square root of T2 by T1. So, B1 by B2, so B2 by B1 by 2, so B1 by B2 will be 1 by 2 and T2 by T1 is 4, the square root of 4, that will become 2 by 2 is equal to 1, that means M1 is also equal to M2. So, that means these flows are dynamically similar. Okay. I will just give you one last example and then we close the discussion today. Okay. So, the example is flow in a lead driven cavity, right. So, we have been discussing about this case of lead driven cavity. Okay. So, this is a domain, okay, and there is a cavity which is moving at certain velocity, okay, let us say u, okay, and then you will have flow which gets developed here. Okay, let us say that you want to simulate this flow using a dimensional solver and a non-dimensional solver. So, what is the dimensional solver? That means you have to assign the value of pressure, velocity, length, temperature, all those things. Okay. In the non-dimensional solver, what you need to assign is your Reynolds number and Mach number, okay, and maybe the temperature, right, some scaling. Okay. So, you have the Reynolds number, which is a very famous example. Okay, Reynolds number based on this length scale, this is your L, okay, and your top moving velocity. So, REL equal to rho u L by mu is equal to 400, right, and Mach is given as u by A is equal to 0.1, okay, and the temperature is given. Even if it is not given, you can assume it. Okay, this is 288 Kelvin. Right. So, now if you want to solve this problem using a dimensional solver, for non-dimensional solver you have all the numbers given. Okay. Non-dimensional solver, what you need to do is that just set up the problem in the bonding conditions, give the no slip bonding conditions everywhere. Okay. For the top lead, you just give the velocity which will be in the non-dimensional solver, it will be equal to 1, because you are non-dimensionalizing with respect to the velocity that is moving. Okay. And then just set up the Reynolds number and Mach number. But let us say you want to solve it using the dimensional solver, then you need to find out your velocity, your values of P, V, L, T and also rho, right. So, how do you do that? Okay. This is very easy to do so. Okay. So, you can take any side length L equal to 1, or you can take 0.1, 0.01, it is your thing. So, whatever thing that you want to take. So, let us say I am taking L equal to 1. Okay. Now, the first thing that you know is the temperature, right. So, from the temperature, what are the things that you can calculate? Your mu directly depends on the temperature, the viscosity, and your speed of sound depends directly on the temperature, right. So, use the Sutherland's law, okay, and you know the values of the C1 and S, which are constant. So, you can calculate the value of mu, okay, which will come out to be 1.79 or so into 10 power minus 5 Pascal second. Similarly, you can calculate A equal to square root of gamma RT, and you will get the value of square root of 340 meter per second, okay, which makes sense because the temperature is around 288 Kelvin and you are doing it for air. So, gamma is equal to 1.4, okay, T is 288 K, and R will be around for perfect gas 287 point something, okay, joule per kg Kelvin. Okay. So, that will give you the speed of sound as 340 meter per second, right. So, because the Mach number is 0.1, your velocity will become Mach into A, which is 34.02. Okay. Now, that you know your speed of sound, the velocity and the viscosity, and your length scale also you know, you fix it to 1, you can calculate your density. How? Because REL is equal to rho u L by mu, right. So, if you want to calculate rho, it will be REL into mu by u into L, right. So, if you put all those values there, you will get the value 2.1059 into 10 power minus 4, right. So, you might be finding it very surprised that why the density value is very low, it is not realistic, right. So, it does not matter in CFD, okay, right. You can set up the value, and as long as the value is reasonable, okay, that means it is not going into some kind of floating point error or some error which is like below the precision of the computer, it will run, right. But for the experiments you have to be very careful, you have to choose a dimension L, so that your density is matching to the density of the air or density of the water, whichever medium you are selecting for the simulation, right. So, you have to fix some other things there, and after you got the density, you can find the pressure also, P equal to rho RT, okay, which is basically 17.40599. Okay. So, you can use these values to basically do the simulation using a dimensional solver. You know the value of rho, u, t, p, mu and everything, right. So, this is how you can convert from the dimensional to the non-dimensional and vice versa, right. So, in CFD it is pretty easy because you are not really bothered about what is the actual value of density or actual value of pressure and how it matches to the realistic situation. But it is very difficult in an experiment to basically get the dynamic similarity 1-to-1 between what is happening in a realistic condition and what is happening in your wind tunnel condition. Okay. For example, you want to match both the Reynolds number and Mach number, and often it is not very easy to do so. Okay. So, in that case what we do is we talk about the partial similarity, in the sense that let us say even you are not able to do at a very low Mach number. Okay. Let us say you are not able to do at Mach equal to 0.1, right, but if you can do it to let us say Mach equal to 0.2, but by maintaining a similar Reynolds number, you can assume that flow to be nearly similar, right. So, you can have this kind of partial similarity in your realistic experiments in the in wind tunnel, but in CFD you can basically find out the values of the primitive variables and do the simulation. And remember, this is not the only way to do that. You can basically change your length scale, you can change your viscosity, okay. You can fix your different temperature and you can get different values of primitive variables. Okay. So, with that we will conclude the talk today. We will meet in the next lecture, where we will non-dimensionalize the governing equations. Thank you very much.